My name's Aaron, and I have a little bit of an interesting background. I think that's not typical of a developer where I'm at. I started in physics and music. So my undergrad is in physics, and I studied music, jazz, trumpet, composition. And I got into this space by picking up a book about C sound, which was kind of a gateway drug into things. And I actually took a summer workshop one year as a high school teacher at UC Berkeley at SynMat, and learned about Maximus P, and then kind of just kept following the black hole all the way down. From that experience, I actually met folks who are working on this game nearby at Maxis. And my first game job was actually writing procedural music on Spore. So actually, my first paid game job was writing PD patches all day, which is kind of crazy. After that, I went back to graduate school at UC Santa Barbara and uh, got a degree in media arts and technology there. Did a bunch of other crazy art projects there. And then after that, I went back into games. Had a brief stint as a sound designer working on Dead Space, where I made crazy horror sound effects. And then because I could code, it was hard to resist the lure of being an audio programmer. And then I was an audio programmer in a bunch of games, and then I landed a gig at Epic about 11 years ago. So I've been here at Epic, and I was the first audio programmer that they had hired. And since then, we've built the team up. I think we have about 14 audio programmers now. And so I'm pretty proud of the work that we've done at Epic for audio. And some of this is a continuing story of that progression. So before I go into the topic of what this talk is about, which is this concept of channel agnosticism, I want to give you some background and context if you're new to what our tech does and what we're all about. Feel like this might be a primer to kind of spark your interest. I'm here not to give a big workshop about how MetaSounds work or how any of our game audio tech works, although maybe next year I'll do something like that. But this kind of will give you a taste of what it is if you're not familiar with it, and there's plenty of resources where you can follow up after this talk when you go home to learn more about it. So, thinking about how to dive into this, I'm going to start at the Unreal Engine, which is obviously the technology made by Epic Games. If you don't know, Unreal Engine is used by tons and tons and tons of games, including Epic. We make our own games. You might have heard of Fortnite. Um, and it's relevant in the context for this audience because I kind of like to think of it as software that makes software. Games are software. And so you can think of it as kind of like a digital audio workstation that makes digital audio workstations in a way. And It's kind of an interesting paradigm. But the main takeaway is that the end product is not a static artifact. Like a DAW kind of has a static artifact as the output. The artifact that is made by a game engine is interactive software, which fundamentally changes your approach to making software in development. And itself can host plugins. The idea of like a DAW plugin is kind of cute from the standpoint of what plugins mean in the context of Unreal Engine. A plugin can fundamentally extend the underlying tech in ways that are fundamental. MetaSounds, a thing that you know about, I'll go into detail in a second, is itself a plugin to give you an idea of the level of magnitude of what plugins mean and the extensibility it implies. It's also obviously not an audio tool. It's kind of an obvious thing to say. But it's relevant to this audience from the standpoint that there's a bunch of other content creators in the tool set. So the idea, like a DAW, primarily caters to audio people. Unreal Engine caters to many departments that have very deep technological depth and uh, complexity, and provides opportunities for really interesting collaborations between domains. Or if you're an auteur that can do it all, you can do it all in one tool set and make crazy audiovisual experiences. And I think it's actually a relevant, unique thing about Unreal Engine as a creative tool set. And it's used for things other than games. So there's a huge market. Epic is pushing into virtual production, architectural visualization. There's a lot of stuff with live shows. People are doing live shows with Unreal Engine. We're doing collaborations with Deadmau5, for example, recently. And people also use it to make experiences. I put it in quotes, but installations and kind of new media kind of stuff. And people also are using it to make albums. People are publishing interactive albums on Steam. Some people are using it to actually make traditional static albums, which I'll give you an example in a second. But anyways, it's a tool set that I recommend people check out from the context of this conference. To go a little bit deeper, the audio engine inside Unreal Engine is a fully featured AAA audio engine. It supports very large content teams. We have 100 sound designers and content creators at Epic ourselves. We're publishing massive amounts of content every couple weeks. We have lots of games that are being shipped with Unreal Engine with our audio tech. From an audio technology standpoint, we try as much as possible to make every aspect of our audio engine extensible. So if you have an idea on how to do spatialization or occlusion, propagation, crazy DSP effects, or any other kind of experimentation, it's an ideal environment for that. It's all the codes there. It's in C++, and easily extensible. And then the other kind of last bullet on this is that audio philosophically has a seat at the table in a tool like Unreal Engine, which I think is really relevant for what we're trying to do at Epic. And then going deeper, MetaSounds is our sort of marquee feature that came out in UE5 for audio. It's, in a nutshell, the vision of what we're trying to do here is to bring the concept of like customizable non-fixed pipeline DSP flow graphs into the context of a mainstream game engine, so that the kind of things that you're used to with Maximus P or PD or Super Collider, all these audio domain-specific languages, can actually have expression in a mainstream game engine, and you can kind of build your own audio experiences and maybe make a lot of money. I don't know. And the other thing is that MetaSounds, the product vision there is also that MetaSounds need to be designed to support content production at scale and also shipping at scale. That means across all of the platforms, and has to support all the stuff that you would expect it with that. And then the other vision is that MetaSounds, we hoped, would be kind of like how Maximus P and some of these other platforms are like crucibles of creativity and experimentation. Kind of wanted the same sort of thing, but in the context of a game engine. So if you haven't seen MetaSounds before, this is my take on the THX sound for our audio tech. This will, when I push play here, it'll show a graph. And the thing to look at, besides the cool sounds and the visualizations and stuff, is that there's a rotating UE logo in our 2D oscilloscope. So basically with this, you can see that, it's a full DSP graph. It has live visualizations. The connections light up. One of the visions for the UX was to make it look like Star Trek's positronic brain, or data's from Star Trek's positronic brain, where it lights up as things are happening. And there's a lot of power for it. I wanted to pick a fun example of somebody from the community. I reached out to this guy, Charles Matthews. He made a ridiculous album earlier this year that he calls Rat's Nests Index Zero. I don't know how to pronounce that, but you can check it out on Bandcamp. But he also has a whole bunch of YouTube videos. And I just wanted to show that people are using MetaSounds to an extreme degree that I would call a rat's nest. And I think it's kind of a funny example here. You can kind of see as he zooms in. I don't know if this is an advertisement as much as it's a horror show, but the point is people are doing crazy things with it. But it's also used in games. I picked a couple ones. Fortnite, as I mentioned. Arc Raiders is turning a lot of heads. Arc Raiders uses our audio tech. And Expedition 33, which came out over the summer. They have a big article that they wrote about how they used MetaSounds. The people who made Expedition 33. So there's a lot of games. I just picked a couple. These are really good sounding games, so I'm proud of the fact that they used our audio tech. Even Fortnite sounds good. Just a little bit extra detail since this is an audience of audio programmers. So the DSP, so what is the MetaSounds and sort of a little bit under the hood briefly? I'm going to be fast on this. It is C++. There's no virtual machine. The nodes are direct into native code. The graph itself is abstract. It could be used for source generation, which is how we're using them now, aka MetaSound. But they could be used for effects processing. In the future, we plan on doing MetaSound effects or MetaSound submixing so that you can use the same underlying technology for all aspects of our pipeline. It's block-based. It's not sample-based. So it is, I would say it has the implied performance in aspects of what that means. Despite the fact that it's block-based, we actually do support sample-accurate triggering, and we have plans of adding sample-accurate data, so you can actually schedule events to happen sub-block. It's not all consumed at the block boundary. I have a little example in code how that works. The node API is extensible. Plugins can add their own nodes, and fundamental types can be added. It's compiled at just in time, so the MetaSound, when you play it in the game, it actually compiles the graph, which has a lot of power. So it can make decisions right before it compiles based off of the context of the game. There's also a runtime API that lets you procedurally build MetaSounds. So games themselves can be constructed around building graphs, which you'd be surprised at the number of applications on that. Data is passed around by reference. Of course, it supports all the platforms that Unreal Engine supports, which is no small thing. There's a lot of platforms that you as a developer would not easily get access to get like PlayStation or Nintendo development kits. It's not cheap. And so if you were to implement something in MetaSounds, it would just work everywhere that a potential customer would use, and you wouldn't have to worry about it. There's a huge amount of built-in node library that we have. I thought this was funny to do a GIF of just scrolling through our documentation, but you can check it out. This is growing all the time. This is what the code might look like for a little fragment. This is one of the nodes we have called a AD envelope, attack decay envelope. At the top left, you'll see this trigger right here. You can see that in my mouse, right? Yeah. So trigger there, that's a sample accurate trigger that comes in that could happen at any point in the block. And the trick to actually service that event is to split up the render block using this sort of sub lambda. And so you have a trigger and you say execute within block and you provide 2 lambdas, which is sort of the amount of audio to render before the trigger happens within the block, and then the amount of audio to happen from the trigger to the next trigger within the block or to the end of the render block. And so with this, you can kind of do your state management. It's still block-based. You still have to deal with sort of non-modulo 4 samples if you want to do SIMD operations, by the way, we have a built-in SIMD library that's really easy to use for audio that we've built out. So all of that kind of works out of the box. But it's a trick, and it works pretty well. And I think it's a pretty powerful feature of MetaSounds. All of our sources on GitHub. Check it out. You have to sign a EULA, but it's free. But it's all there, including the experimental code that I'm about to talk about in a second. There's a ton of learning resources. Check out the Epic developer community. It's probably the best place to go. There's a whole bunch of official docs. We also have an AI assistant, like an official Epic AI assistant that's trained on our code. I hear it's very good. I haven't used it much, but I've heard people describe or tell me that they've been using this to actually auto-generate MetaSound graphs, and it works. And the other thing I recommend, this is unofficial Discord server, but it's very popular. There's a lot of people there. I hang out there when I can. A lot of people on my team hang out there. I recommend it. It's a really positive community, not just for audio, but for all of Unreal Engine. And they have 125,000 members, so it's a good place to get connected and meet people that are doing stuff in the tech. This is an article I want to highlight. This is on the Epic developer community. I wrote this a couple years ago, I guess 2022. It's a little outdated, but I've asked the community if it's still useful, and they say it is. So I need to update it. The APIs have changed a little bit, but if you sync back to the Unreal Engine version I described there, it should still work. But it kind of describes in extreme detail, it's a very lengthy article, the process of making a non-trivial MetaSound node. I actually build like a granular pitch shift node. Kind of talk a little bit about the DSP if you're interested in how that works as well. And then I added this slide yesterday talking with some folks, but to really underscore the idea that MetaSounds is extensible, Cycling 74 themselves, a couple devs there, actually made a bridge that automatically code generates MetaSound nodes from an RNBO export from Maximus P. If you don't know what that is, go check it out. But basically, they have a workflow where you can have Maximus P open, build your graphs, export it as an RNBO file, has a file watcher over in their plugin here that auto generates MetaSound nodes. And so if you have the Unreal Engine open, it can automatically hot reload the code from underneath the Unreal Engine while the editor is running and have the RNBO code reload into the game live. It's pretty impressive, and it works. But it's experimental software, so caveated. But it's an idea. The point of this is that it's, people are doing stuff with our tech that you should be aware of and maybe add to it and do cool stuff too. All right, so final slide on MetaSounds. I'm trying to go quickly through this, but basically what makes MetaSounds different than Maximus P, I'm just going to rip through this really fast, although it's a really wordy slide. But MetaSound graphs themselves are instanced. One of the big things, if you're used to Maximus P, is thinking about your graph as like a singleton mega thing. Like I'm going to make a piece. MetaSounds, there's hundreds of them running. They're all instanced. The graphs are all spatialized. So kind of have to rethink of your idea in terms of smaller pieces of code working together or graphs working together. As I already mentioned, it has sample accurate events, which is a very powerful feature. It supports this idea of data interfaces. So your graph has this sort of inputs and outputs that can be easily connected to the game, which is a pretty important thing. So like game data can feed into your MetaSound, and also MetaSounds can feed data back into the game. And it goes one step further by adding an interface that can be queried and enforced. So you can make like a gameplay system, like a vehicle system that only allows MetaSounds to implement a matching interface so that your content can kind of plug and play and match up. The big idea of MetaSounds is that it's the sounds of the metaverse, and this is a crucial idea for interoperability. So your MetaSound that you've made for a particular subsystem or gameplay system could theoretically be plugged into a gameplay system that you didn't even know about, but maybe there's a enforced interface that allows those two systems to talk to each other. There's also this whole system about preset generation. So you build a base graph and then you reuse it fundamentally, and it's out of the box. There isn't like any kind of crazy fancy stuff. I know Maximus P supports presets, but this is just out of the box. And also graphs are versioned, so it has a versioning system. So the sound designer makes a graph and then someone makes a bunch of presets off of it, and then they go back and change the base graph. It'll propagate automatically to all the reference presets. And you can even do major and minor versions as a content creator, so you can kind of force people to upgrade the content. There's also a bunch of scalability tooling. So that means like you build a crazy graph for PlayStation 5, but it needs to also run on Switch. And so you can kind of make a cheaper version and have it swap out dynamically to a lower quality version. And then, as I mentioned before, there's a procedural API that allows you to build graphs at runtime. I don't think that is a thing that exists elsewhere. So there's things that are unique about MetaSounds. Anyways, it matters because we're making games. In a nutshell, we have large teams. You're making stuff at scale very quickly. All right, so MetaSounds are great, but there's a critical flaw, and that's channels are rigid. First version on this, the current version of it, assumes mono buffers. This is a huge problem because although it's intuitive, that's how Maximus P kind of works out of the box. It's a huge problem in terms of the stated goals of MetaSounds. So you have really complicated graphs you got to manage. You can't easily reuse graphs because you've got different variations based on the number of channels, like how many channels in your audio file. What is the output channel count? There's all this sort of complexity on dealing with mono buffers as your fundamental audio type. Transcoding between different types, like say you have a stereo file, but you want to output 7.1, it's like the sound designer has to deal with that. And it's really annoying to connect to different related audio assets. Like we've got audio files, audio buses, submixing effects, all these kinds of things. It's a really complicated environment. And the audio channel problem was severely underestimated when we started building MetaSounds. And so these are some examples of what it looks like. If you've done a lot of Maximus P programming, this should be familiar. But like on the left here, you can see there's a stereo wave players trying to go to a mixer, and you got to like manually get all these stereo audio outputs to go to a stereo mixer. If you later change your mind that you want to do a mono player, then got to worry about, or if at a 7 point, there's just all this complexity. The graph gets topologically locked to a particular channel configuration. On the right, if you want to do like a filter on all of the channels, you got to sit and add the filter for every single channel. It's a endless nightmare. And on the bottom here, you can see these are MetaSound patches. There's a similar idea, Maximus P abstractions. You can kind of do the same thing in MetaSounds, but you'll see sound designers will go make all these crazy variations of the same underlying logic, but for all possible channel configurations, which is just a nightmare to juggle with. So it's a huge problem. So the question then is, what if we encapsulated the channel in a format data? Like, what if we put it into an abstraction, bundled it together with essentially metadata that described what it is? And that's where we came up with this idea of channel agnostic types. One of the original names was format-agnostic types, and then we couldn't decide if it was format or channel agnostic types. So we would say fat/cat, and then which we chuckled at, we like the fat cat system, but we ended up just calling it cat, channel agnostic types, because that's ridiculous. So the high level goals of cat, one wire, but supports any format or one type. Instead of mono audio, it's just audio. It encapsulates all the relevant data. The primary goal is to simplify graphs and graph authoring, and then to make it actually not just scalable in terms of content creation, but also scalable in terms of performance. It's easier to deal with downscaling channel formats for lower end platforms without having to completely swap out and do all this crazy graph reauthoring. And then the idea is that we also want to make it such that it can support future formats that we can't even imagine, or custom formats. So we started with this idea. This is a lot of debate. This is like endless, like programmers in a room debating like Greek philosophers and how to approach this. We kind of settled on basic three main polymorphic subtypes. Polymorphic means that you can kind of have a derived type and move it around the graph as if it's the, base type. Basically, it's polymorphism, but with channel types. With three main base types, there's discrete channels. If you know about audio, this is not surprising. This shouldn't be rocket science. But discrete channel formats would be all of your regular, like my channel is the left channel, this channel is the right channel, et cetera, all the way up to Atmos type height channels. But also, this is where we plugged in object-based formats. So we kind of consider that to be a discrete channel. And then the other type of family would be sound field. That'd be like ambisonics, all your first order ambisonics, the higher order ambisonics. And then we had this sort of idea of a composite family type where it's like supports a number of different things, like maybe a hybrid, maybe it's partly ambisonics with like an LFE channel that kind of goes along for the ride. Maybe it's some kind of custom thing that doesn't exist. Maybe it's some kind of stereo layering system. Maybe it's stuff that we can't even comprehend in the future. So that's the sort of underlying types. And the other thing that's important here is that each of these things essentially have the audio data and metadata to describe what it is, including like channel location in space. So it would be like 7.1, but like what, where is your left channel in terms of your channel setup, in terms of like the azimuthal degree. And then there's this big idea of transcoding. So going from one family type to a similar family type is generally pretty straightforward. So like a discrete to discrete transcode would be, automatic upmixing and downmixing according to, downmix and upmix matrices. You could use standard channel maps or data-driven custom channel maps. And then from discrete to sound field and sound field to discrete, you'd have your classic sound field transformations, and you'd be able to take your metadata about the channel locations and then do the encoding and decoding from sound field. And of course, if you go from sound field to sound field, I don't have that on here, but that would be generally pretty trivial to do that. And then composite to discrete and back and forth and composite to sound field. You kind of do the same thing, but you provide custom transcoding. And the idea is that if the format conversion is compatible, it kind of automatically happens under the hood. But if you need to go from one subtype to another, you have to do a discrete, not a discrete, but a deliberate manual transcode. And then the big problem that we ended up, like, this took a long time to debate, is like when we initialize the format of these types. This is a big deal. So graphs running, like you have a wave player, maybe one version it's mono, and then you play it again and it's stereo. Do you change the underlying cat type while the graph is running? We decided that was insane. So the basic approach here is that we initialize the underlying cat types within the graph at form initialization, basically when the graph compiles. But it does allow you to delay that initialization up to the moment that you play it, because as I said earlier, MetaSounds are compiled on the fly. So you could actually have game data feeding like wave assets into your MetaSound. And then at the moment of compilation, you could look at that and say, oh, this is a bunch of stereo variations. So this wave player is going to initialize itself to stereo, like the minimal channel types for the graph. There's also this idea that you could set it a priori ahead of time, so you can just have the sound designer say, this is always 7.1, this is always 5.1, et cetera. Let's see. I'll also have it scripted so that we have this builder API. So the builder API could say, hey, this one's always going to be of this particular channel type. One of the things that I wanted to highlight here is the comparison to Max 8's MC signal bundle, if you're familiar with it. I actually learned about this after we had already been internally talking about channel agnostic types. Someone was like, that kind of sounds familiar to this thing that's new in Max. And I was like, what? Did they beat us to the punch? And so I went and checked it out. I love this idea. I wish it existed when I was doing a lot of Max scripting, but it's different. So in a nutshell, what an MC signal bundle is, it's just a multi-channel signal bundle, and it does what it sounds like. It's like a type that bundles a bunch of audio together. It's if you're familiar with Super Collider, it's, I think, analogous to like channel expansion in Super Collider. It's kind of a similar idea. So instead of like manually writing a bunch of code that's like apply this like filter to this audio, you can kind of like automatically expand the channels if you want to make your Super Collider script match multi-channel formats. And I believe, I didn't talk to anybody from cycling about what their motivations are, but it seems pretty clear. It's to simplify the graphs. Makes it easier to, actually the docs say this makes it easier to work with audio spatialization, complex synthesis voicings, and explicitly polyphonic signals. It's similar motivations, but there's differences. The MC signal bundle doesn't have metadata about what it is. It just assumes like a flat discrete channel, and it's up to you to know what's in it and how to deal with it. So it has like essentially different end goals, because Maximus P graphs aren't in the context that MetaSounds are, with this sort of crazy idea of like plug and play the same graph in crazy different contexts. So anyways, so it's different. So this is what the work in progress simplification is. As you saw before, the mixer node would have to deal with all the different, channel inputs. Now it's just a single cable, and what could be in there could be a crazy format of like 12 audio buffers. On the right, here's a details panel that shows up that is also related new tech in MetaSounds that allows you to do channel node configuration. So if you selected the mixer node there, you would be able to have these options, how many inputs are mixing together, and then what your policy is on combining, because each of those inputs could actually be of different cat types. So how do you, like, if the input 0 is mono and input 1 is 5.1, what's your policy on mixing those together? And that's what these little enumerations give you. And you can still work with regular mono buffers. That pink type is our regular mono audio buffer, but this is a little azimuthal panner. It's essentially allows you to just, have the graph pan, but the configuration could be determined on what your actual output configuration is. So it could be stereo, or it could be 7.1, or it could be some other format. I do think it's kind of funny that this azimuthal panner has Atmos configurations on it, but under the hood, it's actually a full VBAP. This is just specialized to be a azimuthal panner. But it kind of gives you an idea of like mono gets translated into a cat type here. And then you can in Unreal Engine and Blueprints, there's this idea of a make and a break node to like basically make a struct or a complex object from a bunch of data, and then you can break it back up in Blueprint. Blueprint, by the way, is our scripting language for Unreal Engine. That's not related to MetaSounds, but kind of using the same language here where you can make from pure mono buffers, you can construct in the graph a channel agnostic type. And similarly, you can break it back out. So if you need to like do a bunch of mono buffer processing and then put it back into a cat type, you can still do that. And then up on the top right, here's an example of a casting node. We call it casting when you're transcoding it from one to another. And you can do a cast to a totally different family type. And then the transcode methods, the similar detail panels that you get exposed to. So I'm actually doing really great on time. Sorry if I'm talking way too fast. I was worried I had too much to go to, but I'm at 30 minutes now. So I do want to. I made a cool demo of this using a granulator. So this is what this is. It's a brand new node, by the way. This is a thing that I've been wanting to do for a while. This is basically the patch. On the top right up here is the actual granulator. I can zoom in a second. But that's the actual granulator object. And the rest of the stuff on the left are like parametric manipulations. One of the cool things about MetaSounds, again, re-emphasizing this, is sample accurate triggers. And so in the context of granulation, that gives you a lot of power for spawning grains. Most granulators that I'm aware of have like grain spawn parameters like grain density or grain rate or things like that, where it's sort of an indirection. In MetaSounds, though, you can trigger arbitrarily when a grain can spawn, and then you can have very precise control, of your granulation. And also means that when you decide to trigger a grain, you can actually route that event to pick other parameters per grain. And so you see down grain panning, which is right in the middle. I think I've got right here. On the left, you get a trigger event to see this new grain that happens right here. It's kind of hard to see on this, I apologize, but there's a trigger event and it has a random parameter that does like a sort of spatial offset on the sort of spatial position. So you can kind of create clouds that move around the sound. And then the granulator here, to zoom in, the output there is a channel agnostic type. I have this in this demo breaking to stereo because I assumed I wouldn't have surround sound. But what's cool about this is that this actually works in any channel configuration trivially, which is really cool to have your, surround grains just like flying through space. My office at work has got a full Atmos setup, and it's cool to hear the grains flying all around without like fundamentally changing your logic of your graph. So that's what this is, and I've got a demo here. Oh, this is the actual audio file in my demo. I also wanted to show off our new wave editor tool that we have built in. So that wave editor tool is built into Unreal Engine, and it has a kind of cool features where you can actually stack together, and it's extensible wave operations, so you can kind of automate destructive edits to target different platforms, and you can kind of stack them together. So it's kind of cool. All right, so this is the granulator playing with the channel agnostic types and sort of me DJing and trying to make cool sounds. That's 900 BPM. I'm also proud of the CPU in the top left. You can see it's 1% CPU. Okay, now we're at the 4% CPU. But anyways, so the kind of is a fun application of what it could mean and showing off granulation. Hopefully you like that. Maybe it's the right audience for it. All right, so where are we at now? Where do you want to take this tech? So it's a work in progress. This stuff is checked into our main branch, but it's in the experimental MetaSound plugin. It's actually a good thing to check out, so you can see how we are adding technology to MetaSounds in yet another plugin. So you can have plugins written that depend on other plugins. It's like a whole plugin dependency chain. And so we've got a plugin that we put into a experimental thing so that like it doesn't actually accidentally make it into Fortnite before it's ready. We learned the hard way on this one. Like, what are you doing? Don't use the grain delay, that kind of a thing. Check it out. We've been working on it this year, I would say, is kind of when we started breaking ground. This summer, we had an early version in 5.6. We had a whole bunch of stuff over the summer to uh, refactor some ideas in it. And so it didn't quite make it into 5.7, but 5.8, which is the next engine version, should have all the stuff that you just saw. Our near-term roadmap is to like do a lot of testing. We've got QA teams that are going to try to test this in all these crazy formats, and we want to make sure that it's rock solid before we quote go wide. We have a whole bunch of nodes that exist in MetaSounds, that giant list earlier on, where it's like all these nodes, we're probably going to have to refactor all of them. So before we go into that work, we need to make sure that this stuff actually works well. And then we think of all the edge cases. And one of the big things is connecting it with the rest of the Unreal Engine all the way down to hardware. One of the ideas is that we want to have the cat type concept go all the way from like the endpoints from the lower level like hardware interface all the way to the importing of audio files, everything, so that there's a kind of unified approach to dealing with channel formatting. It's going to be a lot of work. Yeah, so and then we want to add it to all of our stuff when it comes to spatialization, mixing, and all that kind of stuff. The other thing I wanted to leave, this is kind of last big slide on this talk, is kind of opening the idea of this concept beyond Unreal Engine. So cats are kind of like an internal solution to dealing with all the craziness of channel formatting, but there's what we kind of think about as the edges, like where you have an audio file that gets ingested that might be described by ADM, sort of a data description. Here's this audio file. Here's where its metadata is, and then you have codecs and bit streams that you encode for, just regular old surround sound, but also MPEG, Atmos, that kind of thing. And so maybe cats could be a kind of interface between those extremes for, more intelligent content interoperability. I think it's a generalized problem. I think DAWs also struggle with this problem. It's a nightmare of formats. So I'll leave this with you thinking about the metaverse. This is it's like kind of a dirty word, but at Epic, it's a driving principle of where we're trying to build our tech. We think a lot about what does it mean for content to be created in an interoperable way. A game might be able to make content for its experience, but maybe publish its content so that it could go into some other experience. So what does that mean for asset transfer, especially in the context of interactivity? And so there's a lot of thought in that space, and that's what we're trying to solve. And I'll end this on acknowledgments. So I don't want to leave the impression that I'm the only developer here. As I mentioned earlier, there's a big team. We actually have 2 core teams at Epic, the Unreal Engine audio team, which is the one I'm on. We also have an audio gameplay team that focuses a lot on support for Fortnite, but they also do a lot of core development in all of our tech as well. So they deserve a lot of credit, and our collaborations allow us to be able to do this kind of stuff. I also want to acknowledge all of the input and abilities of our technical audio designers. We have a whole bunch of them, and they are heavily influential in the direction of our tech. So I want to acknowledge that. And of course, our content creators. We have a whole bunch of audio directors and designers using our tech, giving us feedback. We also have a lot of support from product. We have a product manager who gives us say, hey, let's think about the user, the end. What is the user experience of this, and have sort of a unified vision as much as we can. And then, of course, production and QA are huge for our stuff. And I want to have a special acknowledgement. I'm not the lead developer on Channel Agnostic Types. Jimmy Smith, he wasn't able to make this talk, but he is our senior audio programmer who is the lead developer and implementer of Channel Agnostic Types. He's the person I spent a lot of time debating with. So I just want to give a shout out to my team. And that's it.